Have you ever dropped a ball and watched it fall? Of course you have. You'd say gravity pulled it down. But what if I told you there's no such thing as a pull? What if the ball isn't being pulled at all, but is actually just taking the straightest possible path through a curved universe? Sounds wild, right? Well, welcome to Albert Einstein's general relativity, one of the most mind-bending and beautiful ideas in all of science. Today we're going to unravel it, not with complex math, but with simple, visual ideas. By the end of this video, you'll see the universe in a completely new light. Let's start by rewinding the clock a bit, back to Sir Isaac Newton. For over 200 years, Newton's law of universal gravitation was king. He imagined gravity as an invisible force, a mysterious pull that every object with mass exerts on every other object. The more massive the object, the stronger its pull. The Earth pulls on the apple. The sun pulls on the Earth, keeping it in orbit. It works perfectly for sending rockets to the moon or predicting tides. It's a fantastic description of what gravity does. But Newton himself was bothered by a big question. How does it do it? How does the sun, 93 million miles away, tell the Earth to stay in orbit? How does this force act instantaneously across the vast emptiness of space? Newton had no answer. He famously wrote, "I frame no hypotheses." For centuries, gravity remained this mysterious action at a distance. This is where a young patent clerk named Albert Einstein enters the picture. In 1905, he published his theory of special relativity, which dealt with the relationship between space and time for objects moving at constant speeds. But that's a story for another day. What's important is that special relativity revealed something profound. Space and time are not separate things. They are interwoven into a single, four-dimensional fabric called space-time. Think of it like this. Normally, we describe a location with three dimensions: length, width, and height. To arrange a meeting, you'd say, "Let's meet on the 5th floor, height, at the corner of Main Street, length, and Oak Avenue, width." But you're missing a crucial piece of information. When? Without a time, your friend won't be there. So to pinpoint any event in the universe, you need 4 coordinates, 3 for space and 1 for time. This is space-time. Einstein spent the next decade wrestling with how to fit gravity into this new picture of space-time. He had what he called his happiest thought. A person falling from a roof wouldn't feel their own weight. In that moment of free fall, for them, gravity would seem to disappear. Imagine an astronaut in the International Space Station. They're floating, weightless. Is it because they're far from Earth's gravity? Not at all. The ISS is still very much in the grip of Earth's gravity. The reason they're weightless is that they, and the station around them, are in a constant state of free fall around the Earth. This insight was the key. Einstein realized that gravity isn't a force at all. It's a consequence of the geometry of space-time itself. Here comes the classic analogy, and it's a great one. Imagine a flat, stretched-out rubber sheet. This sheet represents our four-dimensional space-time. Now let's place a heavy bowling ball in the middle. What happens? The sheet warps and curves around the ball. The heavier the ball, the deeper the curve. This is exactly what Einstein proposed. Mass and energy tell space-time how to curve. A massive object like the sun creates a huge warp, a deep well in the fabric of space-time. Now, what happens if we roll a smaller marble nearby? The marble isn't being pulled by the bowling ball. It's simply following the straightest possible path along the curved surface of the sheet. From our perspective, it looks like it's orbiting the bowling ball. And that's it. That's general relativity in a nutshell. Planets orbiting the sun aren't being pulled by a force. They are following straight lines called geodesics through the curved space-time created by the sun's mass. The Earth thinks it's traveling in a perfectly straight line, but the space it's moving through is bent. It's like a pilot flying straight over the Earth's surface. From their perspective, they're going straight. But from space, you can see their path is curved around the globe. This isn't just a prettier theory. It makes predictions that Newton's laws can't explain. One of the first confirmations came from the orbit of Mercury. Astronomers had known for decades that Mercury's orbit wasn't a perfect ellipse. It wobbled slightly with each trip around the sun. Newton's theory couldn't fully account for this wobble. But when Einstein applied his equations, they predicted the wobble with pinpoint accuracy. It was caused by Mercury moving through the deeply curved space-time close to the sun. But the most spectacular prediction of general relativity is that gravity can bend light. Remember, light also travels through space-time. So if space-time is curved, the path of light must be curved too. Imagine a beam of light from a distant star passing near our sun. The sun's immense gravity warps space-time, and the light's path is bent as it follows that curve. This was a radical idea. In 1919, during a total solar eclipse, the astronomer Sir Arthur Eddington set out to test it. By photographing the stars near the eclipsed sun, he could see if their apparent positions had shifted, and they had, by exactly the amount Einstein's theory predicted. This made Einstein an overnight global superstar. The headlines read, "Lights all askew in the heavens, men of science more or less agog." The effects of general relativity don't just happen out there with stars and planets. You use it every single day. The GPS in your phone relies on a network of satellites orbiting Earth. These satellites have incredibly precise clocks. According to general relativity, time actually runs slightly faster for these satellites than for us on the ground, for two reasons. First, they're moving very fast, special relativity, which slows their clocks down a bit. But second, and more importantly, they are in a region of weaker gravity, further up in Earth's gravity well, which means their clocks speed up. The effect is tiny, just a few microseconds per day. But if engineers didn't correct for this relativistic effect, your GPS would accumulate errors of about 7 miles every single day. Within hours, it would be completely useless. So, the next time you use Google Maps to find the nearest coffee shop, you can thank Albert Einstein and his curved spacetime. General relativity also predicted some of the most exotic objects in the universe. It predicted that if an object is massive enough, it can curve spacetime so much that it creates a bottomless well from which nothing, not even light, can escape. We call these black holes. For decades, they were just a mathematical curiosity. But today, we've photographed the shadow of a black hole and even detected the ripples in spacetime, gravitational waves, created when two black holes collide. These are direct confirmations of Einstein's 100-year-old theory. So, from the falling apple to orbiting planets, from the GPS in your pocket to the majestic dance of colliding black holes, general relativity provides the rulebook. It redefines our most fundamental understanding of the universe, replacing the idea of a mysterious force with a dynamic, geometric stage on which the cosmic drama unfolds. Gravity is not a pull, it is the shape of the universe itself. And we are all just following the curves. Thank you so much for joining me on this journey through space-time. If you found this explanation helpful and want to explore more incredible ideas from the world of science, please hit that like button and subscribe to the channel. It really helps us create more content like this. Let me know in the comments what other big ideas you'd like us to tackle next. Until then, keep looking up.